Great day, learners. I am Miss Bethel Grace P. Taban, and I am your official instructor in Agric 44. I am one of the faculty members of the Department of Agronomy and Plant Breeding, College of Agriculture, Central Mindanao University. This afternoon, or this day, I will be introducing to you summation notation. And in the study about summation notation, we will be using a lot of sigma sign or sigma notation. So why is there a need for us to really study about this summation notation? Aside from passing, of course, statistics, you need to know the importance or the application of summation notation in your real life or real life application. But before that, I wanted you to be ready. So please get your ballpen, your calculator, your paper, or any other material which might be helpful in our session today. Okay, let's get this done. Sigma notation, summation notation, sigma sign, all of those terms, we will be using them in our discussion about learning activity number 2. And by the way, summation notation is very important because you will use this extensively all throughout our statistics course. In our adventure in statistics, we will be encountering or we will be using a lot of summation notations. Let us say you were tasked or you were assigned to get the sum of the terms. And these terms have patterns, assuming that you were tasked to get the sum of the first 10 numbers. So it's like saying 1 plus 2 plus 3 plus 4 until you would reach plus 9 plus 10. Then you will derive the answer. Actually, it's easy to do that because you can simply write all the numbers, add them, and get the sum. But what if you were assigned to get the sum of the first 100 numbers or the first 1,000 numbers? Would that be easy? Of course, it's tedious. You need to write a lot of terms. You need to write or input a lot of values or a lot of numbers. So this is where summation notation falls in. It helps us derive to the correct answer, but the solution is not that lengthy because we know the terms and we know that those terms have patterns. We could directly jump into using notations to find out the sum. But before we go directly to the calculations and computations, I would like to remind everybody that in our activity today or in our learning video today, we will be having a lot of problem sets. So before going to those things, before stepping into that arena, let me share to you this quote given to us by Carl Person. According to him, please chew this, swallow, digest, and absorb the nutrients. Statistics is the grammar of science. In your lecture, in Agric 44, for sure, it has been discussed to you that statistics entails collection of data, analysis, interpretation of the data, and presentation of the results. Or how do you define statistics? I hope that by now you can already define statistics. So statistics and science, actually, they are interrelated, right? It's actually the grammar of science because you need to do work in science and you need to communicate these results to the stakeholders. You need to communicate the results to the population or the sample that has been used in order to obtain those empirical data and to process this data for it to be made available for us to create theories, for us to check our hypothesis. Let's say, for example, okay, let's try to relate it to the current scenario about this COVID-19 pandemic. We know that vaccines are already available, and you wanted to know the efficacy of the vaccines. Pfizer, Moderna, or AstraZeneca. Among those three, which is the most effective? So try to check on the statistics per country, per age bracket, the number of positive responses, the number of negative responses, or you wanted to check on the effectivity of a diet program among a selected group of people, whether it's 16:8 in terms of intermittent fasting, 16:8, 12:12, 10:14. What time interval is the most effective and most healthy for most of the population or the sample? Or trying to know which input is very effective in potentially increasing the growth and performance, growth and yield of a certain crop species. Is it using organic fertilizer or using this different synthetic fertilizers? Or in testing, what feed meal ration is best for the performance of the chicks? Or what crop in terms of its nutrient is best in treating or in deworming hogs or swines? So all those things, they need statistics for us to make sound judgment, to create sound decisions. That's why statistics is the grammar of science. And in statistics, it's very crucial to know the rules of rounding off numbers because most of the problem sets in statistics, of course, results from measurements. And this rounding of numbers is very essential, especially if there are decimal places. And talking about decimal values, we really need to have a recap about your basics. So we have here a working definition of the place values and an example. So this is, of course, your decimal point. All of these values here are whole numbers. And this one refers to the different decimal values. So we have here starting with the ones, tens, hundreds, thousands, 10,000s, and 100,000s, so on and so forth. You could reach up until trillion. And then at the right side of the decimal point, we have tens, hundreds, thousands, 10,000s, and 100,000s. Tens is just 1 over 10, hundreds is 1 over 100, thousands is 1 over 1,000, 10,000s is 1 over 10,000s, and 100,000s is 1 over 100,000s. So going to this example, it's 987,654,321 point all of this decimal values. So if you are asked what is the decimal value of 3, then for sure the answer is thousands because we are actually starting with tens. Then when asked what is the number having the decimal value millions, then the answer is 6. Of course, it's 0.000006. So 6. So this is, it's just simple. So ones, it's 1. Tens, so this is 20. That's why 20 plus 1, it's 21. So 3, it's hundreds. So it's 300. So when adding together, 300 plus 20, 320 plus 1, it's 321. So that's how to know the place value of a number. You really need to learn these concepts because we will be using this extensively in statistics. You will be dealing a lot with whole numbers, with decimal places. And mind you, if there are slight changes in your answer on the decimal values, then for sure it could either lead you to a correct answer or a wrong answer. And another thing is that you are actually required to round off up to the nearest thousands or up to the nearest 10,000s or up to the nearest tens or hundreds. So if you do not have any idea on this place value, then it would be hard for you to derive the accurate solution for a specific problem set. So talking about quantitative data, so highlighting why is there a need for us to really study summation notation, because the analysis of this quantitative data entails different mathematical formulas. And of all the mathematical formulas, we have the basics: addition, subtraction, multiplication, and division. The most commonly used operation actually is addition. So this is where summation formulas or summation notation is involved, because most of our transactions in life involves addition or summation. So here's the nitty-gritty about the rules for rounding numbers. So we have the first two rules here. So when the last digit or the digit to be dropped is less than 5, then automatically that digit or that specific last digit will be automatically dropped. So this is actually another review of your basic knowledge in mathematics. So, di ba, in your elementary years, you were taught that if it is less than 5, so less than 5, you are going to drop that digit or to drop that number. So let's have these values as an example. So we were tasked to round off the following values to the nearest hundredths. So nearest hundredths meaning it's 2 decimal places, because we're starting with tenths, hundreds, and thousands. So hundreds. So we have this value here. It's 0.794. So the last digit is 4. And we are required to round this value to the nearest hundreds. So identifying that 7, the place value is tenths, 9, the place value is hundredths. So we are required to round off this value up until this value or this number, which is 9. And 4 is the thousands. So what is the number beside 9? Actually, it's 4. And remember that 4 is less than 5. Thus, we need to drop this off or remove this. So rounding 0.794 to the nearest hundredths, the answer is 0.79. Another example is 5.861. Again, this is, what's the place value of 5? Okay, it's ones. You're correct. 8, it's tenths. 6, it's hundredths. And 1 is thousands. So again, we are required to round this off to the nearest hundredths. So what's the value after 6? It's 1. Obviously, 1 is less than 5. So we need to remove this one. So we're left with 5.86. This is the correct answer. Another value is 0.68363. So nearest hundredths, let's try to identify the place value. 0 is ones. 0.6 is, yes, it's tenths. This is hundredths, thousands, 10,000s, and 100,000s. Remember, it's only nearest hundreds. So we should retain 2 decimal places. So 6, 8, what's the number beside 8? After 8, it's 3. Again, it's less than 5. So we need to drop the remaining numbers. So rounding 0.68363 to the nearest hundreds would give us this answer, 0.68. Okay. Rule number 2 is this one. When the last digit or the digit to be dropped is greater than 5, the preceding digit is increased by 1. So simply saying greater than 5, it should be added with 1. So let's have this as an example. So if earlier we are tasked to round off the numbers to the nearest hundreds, now we are required to round off the numbers to the nearest tens. So going back to this value, 0.79, the nearest tens. Let's try to identify first the place value. 0 is, yes, is ones. 0.7 is tenths. And this 0.09 is hundreds. Ma'am, why do you mention 0.09? Because zero point 0.7 plus 0.09 is 0.79. Told you earlier, that's how to read place values. It's 1 over 10, and for the place value of 9, 1 over 100. So converting or rounding 0.79 to the nearest tens, the answer is, yes, you're right, it's 0.8. Now another example is 9.89. So this is ones, tenths, hundredths. So the nearest tens, 8. After 8, we have 9. 9 is obviously, again, greater than 5. So we are left with 9.9. 70.476. So we are going to round this off to the nearest tens again. So 4 is 0.4 rather is the 10th, having the 10th place value. So after 4, we have 7. So again, 7 is greater than 5. So we are going to add 1. So it will become 17.5. So as easy as that. Again, this is just a recap of your basic or general knowledge in mathematics. The third rule is when the last digit or the digit to be dropped is 5, earlier we have discussed the digits greater than 5 and the digits less than 5. What if the digit to be dropped is 5? What are we going to do? Actually, the rounding off, if the digit to be dropped is 5 or the last digit is 5, this is governed by the even integer convention. It's simply rounding off to the nearest even integer. So let's have this example. Round off the following to the nearest thousands. So 0.4385. So let's try to identify first the place value. 0 is ones. 0.4 is tens. 0.03 is hundreds. 0.008 is thousands. And 0.0005 is 10,000s. So tens, hundreds, thousands. So 3 decimal places. Please notice that after 8, the number is 5. So the digit to be dropped is actually 5. 8 is an even number, right? Even number, recalling 2, 4, 6, 8, 10. All of those numbers are divisible by 2. So it's even. Since it's even, we just need to omit 5 and retain 8, which is the even number. So we're left with 0.438. Okay, let's have another example. 5.4755. So 5, the place value is, yes, it's ones, you're right. 0.4 is tens. 0.07 is hundreds. 0.005 is thousands. And 0.0005 is 10,000s. So again, 3 decimal places. So we're left with 5. 5, okay, 5 is the last digit. Its place value is thousands. So after 5, we have another number or we have another value and it's the same, no? It's still 5. So 5 is an even or an odd number. It's an odd number. Since it's an odd number, we need to add 1. So 5.4755 will become 5.476 when we're going to round this value to the nearest thousands. And the last example is 0.86354. Let's try to identify the place value. 0 is ones, 0.8 is tens, 0.06 is hundreds, 0.003 is thousands, 0.0005 is 10,000s, and 0.00004 is 100,000s. So we're only required to round up to the nearest thousand. So again, 3 decimal places. 3 is an odd number. And the number beside 3 is 5. Therefore, adding 1 to 3 to make it 4, because this is an odd number. So 0.86354, when rounded to the nearest thousands, will give us this answer, 0.864. Is it hard? Of course, it's not. Okay. It might be challenging, but for sure, with constant correct studying, you will master this. So the rule I stated earlier may be simplified as when 5 is preceded by an odd number, the preceding digit is increased by 1. Notice earlier that the number having the place value thousands is 3, and beside that number is 5. 3 is an odd number. Thus, adding 1, it will become 4. Going back to this example, 0.86354, it became 0.864, right? And then when 5 is preceded by an even number, the preceding digit is retained. So going back again to this example, 0.43858 is an even number, and beside 8 is 5. Therefore, we just need to remove or drop 5 and retain the even number, which is 8. So the answer is 0.438. What if, so we have this, if the number following the 5 is 0, so we could not directly identify even and odd number. What's the rule for this? Okay, here is it. The digit to be rounded is rounded upward if odd, or left as it is if it is even. So again, the same rule is applicable. So let's have this example. 21.550. It says here, nearest 10. So let's try to identify first the place value. Ma'am, we're already familiar with place value. I'm actually highlighting this one for you to really recognize, no? What's the importance of knowing the place value? So what's the place value of 2 in 21? Okay, it's tens. What's the place value of 1? It's ones. How about of 0.5? It's tens. Of 0.05, it's hundreds. And of 0.000, the last 0 is thousands. Because it's like this, 21. So place value of 20 is tens. The place value of 1 is 1. So 20 plus 1, 21. Yes, easy as that. So going back to this example again, nearest tens. So 21.550. Nearest tens is this one, 5.5. So the value after 0.5 is 5. and then it is actually followed by 0. 5 is actually an odd number, thereby adding 1 for it to become, no, actually it's not 1, it's 0.1. Okay? It's just so, no, it's so literal to say 1. But for this one, because the place value is point 0 or 0.5, it's 10. So 1 over 10. Okay? So we need to follow the place values. So adding 1 to make it 21.6. So 21.550 when converted or rounded off to the nearest tens will give us 21.6 as the correct answer. How about 21.450? So nearest tens again, 4 is an even number followed by 5 and we have 0. So 4, since 4 is an even number, we just retain it, or the statement here is left it as it is since it's an even number. So the answer for this is 21.4. Remember in your high school days, when your grade is, when you aim to become an honor student, and for you to become an honor student, you need to get a grade of 85 and above. And then what happened was your grade in mathematics was 84.45. And then you would ask your teacher, Mom, can you please make it 85? And then your teacher would tell you, no, it's not. It's impossible to do that. Then you're thinking like, why? Why is it impossible to do that? When in fact, 84.45, 84.45, it can become 85.5, and 85.5 could become, I rather 84.5 could actually become 85. No, actually, it's impossible because our instructors, basically, they're teaching mathematics. They know the rounding of numbers. That's why 84.45 is just 84. So, hindi ka naging honor student ng dahil dun. So, there are cases like that in your high school days. Or maybe some of you already experienced that, right? Especially if you are studying in a laboratory high school. So, those are the nitty-gritty of rounding off numbers. Now, here's the real deal about summation notation. So, just no, not a warning. This is not a warning. A reminder that all of the time we will be using sigma sign in summation notation. So summation notation, so we have the sigma x, right? So summation, it's simply adding all the elements or adding an array of numbers. So summation, so we have here as we defined it as a value, which is actually the result of adding all the elements of x if you are using x, or if you are using y. Actually, you could use any letter. But for our example here, we are using x. That's why I mentioned x. So adding all the elements of x as in one column table or a single dimension array. So we have here, I wanted you to learn or to practice the skill of reading a notation properly. So we have this notation. This is actually read as the summation of xi. Let me point this out. The summation, because we have the sigma sign, summation. When you see this sign, it's automatically summation. So summation of xi from I equals 1 and I equals n. So any number, okay, as long as it's part of the array. So if you are adding 10 numbers, then it's 1, ranging from 1 to 10. So if you're adding 20 numbers, then it could range from 1 to 20. So it's like this also. So if we're going to expand this notation, summation of xi from I equals to 1 to I equals to n. So it's like x sub 1, the first value plus x sub 2, the second value plus x sub 3 or x3, to make it simple, plus the other remaining values found in the array until you would reach the last value. For this one, we define this as n because you could reach up to how many values. It's up to you. It's up to you if ilang values ba yung i-include mo sa notation. So another definition is that the symbol sigma or the capital sigma is often used as a shorthand notation. Again, this is what I am telling you earlier to indicate the sum of a number. And this number is, of course, of similar terms. In my previous discussion, I've mentioned to you that summation notation, it's easier for us to add those numbers because, or those terms, because they all actually have patterns. And aside from that, sigma notation is used extensively in statistics. For example, let's have this. Suppose we weigh 5 children. So we have here 5 children. We will denote their values or their weights as x1. So this child is x1. The weight of this child is x1. The second child is x2. The third child is x3. The fourth child is x4. And the fifth child is x5. So we are after, since this is summation, we are after of getting the sum of their weights. So how do we write this one? Remember, there are 5 children. So automatically, we have 5 different weights. So how do we write this one in summation notation? So this is the notation that we will be using in order to know the sum of their weights. So the sum of their weights is written more compactly as summation of xi referring to their weights, from I equals to 1, which is the first children, to I equals to 5, which is the fifth children. So if in order for us to read this, the summation of xi from I equals to 1 to I equals to 5. In some other books, you could see I equals to 5. It's very evident that there are only 5 members of the array or 5 values. But in other literature, so this one I am using, what's automatically written here is just 5. So there's no need actually for you to put I equals to 5 because it signifies that there are only 5 values involved in this array. So in order to expand this one, we need to add the different weights. So remember, we have 5 children. So the summation of xi as I equals to 1 to I is equals to 5 is simply adding the weight of the first child, which is x1, the weight of the second child, which is x2, the weight of the third child, which is x3, the weight of the fourth child, which is x4, and the weight of the last or the fifth child, which is x5. So is it difficult? Actually, it's just very easy because the summation tells us to simply add the weight of the 5 children. That's how easy it is to write. So first one is, if you're given a problem set, try to identify the numbers, the members or the values found in the array. And then you are going to write the notation and you should know how to expand the notation. So the symbol sigma, again, means to add up. And underneath sigma, we see I is equals to 1. This one. Underneath or below sigma, I is equals to 1. And on top of it, we see I is equals to 5. This simply means that I is replaced by whole numbers starting at the bottom number, which is 1, until the top number, which is 5. So when the bottom number up to the top number has been reached, it means that's the end of the notation. Thus, summation of xi as I is equals to 1 and I is equals to 5 is simply x2 plus x3 plus x4 plus x5. Why exclude x1? Because this notation tells us that the array or this notation is only starting with the second value up until the last value, which is 5. So there's no need for us to include the first value, which is x1, because the notation is telling us that, okay, you just need to add up the values found on the second value, the third value, the fourth value, and the fifth value. How about this notation? Summation of xi as I is equals to 1 to I is equals to 4. So what are the numbers or the values that we need to include? So only 3 values because 2, 3, 4. So 3 values. So x2 plus x3 plus x4. So if we have this summation notation, we could expand this by giving these values. So the notation, summation of xi from I equals to 1 to I is equals to 5 tells us that there's a need for us to add the scores or to add the weights. That's the xi. Where to start adding? From x1 because I is starting with 1. And where to stop adding? It's xn, where n is some number. For this case, xn is equals to 5. So we need to stop adding until x5. Now, we need to take the weights of the children. Earlier, we just assigned different notations. We have x1, x2, x3, x4, and x5. So let's have a more vivid example. So assuming that the weight of x1 or the first child is 10 kilograms, the weight of the second child or x2 is 12 kilograms. The third child, x3, denoted as x3, is 14 kilograms. The fourth child, denoted as x4, is weighing 8 kilograms. And the fifth child, denoted as x5, is having 11 kilograms as his or her weight. So how do we get the total weight in kilograms? So we already know our notation. It's summation of xi from I equals to 1 to I is equals to 5. Earlier, we have expanded this form. We stated x1 plus x2 plus x3 plus x4 and plus x5. So we just need to substitute the equivalent values or the equivalent weights. So we knew already that x1 or the first child is 10 kilograms, the second child is 12 kilograms, the third child is 14 kilograms, the fourth child is 8 kilograms, and the fifth child is 11 kilograms. So we simply add all of the values in the array. So the answer is 55. So the summation of the weight of the 5 children, x denoted as xi, from I is equals to 1, the first child, to I is equals to 5, the last child is equal to 55 kilograms. As easy as that, right? Now, it's your turn. I wanted you to compute this one. How about using the same data, try computing for the summation of xi from I equals to 1 and I equals to 3, the summation of xi from I equals to 2 to 5, and the summation of x. How do you compute for this summation? So first, try to expand the summation notation. After expanding, try to replace the values given to you. Okay? So in 3, 2, 1. Let's try to answer the problem. So how to answer for the summation of xi from I is equals to 1 to I is equals to 3. Going back to this one, so kindly write down that the weight of the first child is 10 kilograms, the second child is 12 kilograms, the third is 14, the fourth is 8 kilograms, and the fifth one is 11 kilograms. So again, we simply need to add the values pertaining to the weight of the first child to the third child. So it's simply adding x1 plus x2 plus x3, replacing those with 10 plus 12 plus 14. So the summation of xi from I is equals to 1 to I is equals to 3 is equal to 36. And then how about for the summation of xi as from I is equals to 2 to I is equals to 5. So we knew that that second value x2, so to expand the notation, it's x2 plus x3 plus x4 plus x5. So replacing the values or the weights of the children, it's 12 plus 14 plus 8 plus 11. The answer is 45. What if you were given an array of numbers and you were just told to get the summation of x? So the summation of x is just telling us, this is just equivalent to summation of xi from I is equals to 5 to summation of xi from I is equals to 1 to I is equals to 5. So it's like x1 plus x2 plus x3 plus x4 plus x5. Then we are going to replace the value with these numbers 10, 12, 14, 8, and 11. So to get the summation of x, we have this answer, which is 55. So let's try another simple TVT. Okay, I call this hashtag simple TVT. So try answering this summation notation found on top. The summation of 3i, we're not using x anymore. So much for the x, no? Let's proceed with values. So summation of 3i from I is equals to 1 to I is equals to 4. First thing, for us to find the answer, please notice that I is equals to 1, then 2, then 3, and finally 4, right? Because, of course, automatically it would give us an idea that the array contains 4 values or 4 numbers. And those values, we are supposed to multiply those numbers, each of this, by 3. And then we're going to add them up. So the summation of 3i from I equals to 1 to I is equals to 4 is simply 3i. So the first number is 1. So 3 times 1 plus 3 times, what's the second number? 2 plus 3 times 3 plus 3 times 4. So again, try to multiply the numbers by 3 and then get the summation. So 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. 3 times 4 is 12. So adding 3 plus 6 plus 9 plus 12 is 30. So the summation of 3i from I equals to 1 to I is equals to 4 is equal to 30. Lisod? Of course not. Okay. So let's try to dissect the parts. So how about the series? So this is another problem set. Series. We have the series 4 plus 8 plus 12 plus 16 plus 20 plus 24. How can we express this series into summation notation? First is we need to know what's the common term for 4. Again, I've mentioned summation notation, it has pattern. So 4, 8, 12, 16, 20, 24. Notice that these values or these numbers are actually divisible by, yes, it's divisible by 4, right? 4, so 8 divided by 4 is 2. 12 divided by 4 is 3. 16 divided by 4 is 4. 20 divided by 4 is 5. And 24 divided by 4 is 6. So to express this into summation notation, we have this answer. So the expression is read as the summation of 4n as n goes from 1 to 6. Or as n is equals to 1 to n is equals to 6. Or simply saying, summation of 4n as n goes from 1 to 6. So the variable n, this n, the n here, this is what we call the index of summation. And this, the whole of this is actually the formula for the term. So this is actually the term. We know that in this array of numbers, they are all divisible by 4. So we have 4n as the formula for the term. Then we have the sigma sign or the notation. It tells us to simply add. Then n here is the index of summation. 1 is the first value of n, and the number on top of the sigma sign simply tells us that this is actually the last value of n, which is 6. Why 6? Mom, I could not find any 6 in the given array. Let's count off the numbers. So 1. So we have this. So 1, 2, 3, 4, 5, 6. That's why it goes from 1 to 6. There are 6 values in the array, right? So to generate the terms of a series given us in a sigma notation, successively replace the index of summation. Again, what's the index of summation? The index of summation is n, right? With consecutive integers from the first value to the last value of the index. So to generate the terms of the series given in the sigma notation at the left, this one. So we just replace the index of summation, which is n, by 1, 2, 3, 4, 5, and 6. So 4n is equals to, so rather, summation of 4n as n goes from 1 to 6 is equal to 4 times 1 plus 4 times 2 plus 4 times 3 plus 4 times 4 plus 4 times 5 and 4 times 6. So after getting their products, we simply add all of them. So 4 plus 8 plus 12 plus 16 plus 20 plus 24, the answer is 84. So the summation of 4n as n goes from 1 to 6 is equals to 84. Let's have another hashtag simpletivity. So try expanding the following notations. Notice that you could observe different letter assignment. We have used here AI, ZN, and N. But please put in mind that all of these letters or terms are just equal to XI. I just used different letters for you to be familiar that in some other literatures or books, they are actually different, using different letters for different formula or terms of formula of the notation. So try expanding summation of AI as I goes from 1 to 6, or the other way of reading this is summation of AI from I equals to 1 to I equals to 6. Then the summation of Zn as n goes from 30 to 35, and summation of n as n goes from 4 to 7. So here's the answer. Remember that I've only given the formula of the term, but I did not actually give real values or real numbers. So for this notation, summation of AI as I goes from 1 to 6, you just simply use 1 up to 6 in replacement of the summation index, which is I. So summation of AI as I goes from 1 to 6 is equal to AI plus A2 plus A3 plus A4 plus A5 and plus A6. And then summation of Zn as n goes from 30 to 35 is very easy. Zn, rather Z30 plus Z31 plus Z32 plus Z33 plus Z34 plus Z35. I would like to emphasize that if ever you are assigned different values for different arrays, like Z30 is equal to 10, Z31 is equal to 20, Z32 is 8, dot, dot, until Z35 is equal to 5. You use those number and substitute for the different Z values in order for you to come up with a real number as an answer. And then summation of n as n goes from 4 to 7 is very easy. So we know that the summation index is n, so just replace it. 4 plus 5 plus 6 plus 7, which is equal to 22, right? Then we have another simple activity. Write the sum using summation notation. So you are required to write summation notation of the sum from one of the first 100 numbers, from 1 to 100. So to do this, it's very easy. Summation of xi as I goes from 1 to 100, or you could use summation of zn as n goes from 1 to 100, or simply say summation of aj as j goes from 1 to 100. All of those are similar, or all of those answers are actually correct. If you clearly understand the dissection of the parts of the summation index, then you will not be confused. It's easier for you to understand the summation. If you are given the expanded form, you can create a summation notation. If you are given a summation notation, you could expand that. After expanding, if you are given real values, you can substitute the real values to the arrays of the numbers or the terms. Replace that in the formula or term of summation. Now, this one, what does this mean? Summation of 3 as k goes from 1 to 5. What do we have here? A real number. Earlier, we have learned that summation of n as n goes from 4 to 7. So it's simply like 4 plus 5 plus 6 plus 7 is equals to 22. If you could still remember this example, right? Summation of n as n goes from 4 to 7. So we could actually replace 4 plus 5 plus 6 plus 7. So this is 22. How about summation of 3 as k goes from 1 to 5? What's the meaning of this? Yes, because if we write out this notation in full, we get this one. It means we are going to add number 3 repeatedly. Okay? Repeatedly. Like 5 times. So 3 plus 3 plus 3 plus 3 plus 3, or simply 5 times 3 is equal to 15. So summation of 3. So if, for example, you are asked summation of 10 as I goes from 1 to 3. So the answer is 30, because 10 plus 10 plus 10 is equal to 30. Because what's asked is to expand summation of 10 as I goes from 1 to 3. Clear? I hope it's easier for you now. You're starting to get energized and your brain cells are already fueled, no, for you to really learn what is this summation notation. So let me also share to you this hashtag techniques for you to easily understand summation notation. Notice that we have used I in the previous formulas, right? The I is what we call only as a dummy variable. Any letter can be used. For example, summation of xj as j goes from 1 to n, or summation of xi as I goes from 1 to n, or summation of ai as I goes from 1 to n, or summation of zn as n goes from 1 to n, or summation, because my name is Bethel Grace, so like summation of BG as G goes from 1 to N. So you could use any other letter in the formula because those letters in the formulas are what we call dummy variables. So do not be shocked when, oh my gosh, what was given in the learning video was only XI, but during the exam, the professor gave ZN or BG or XJ, and then you were shocked. Tapos you would tell yourself, this was never thought or hindi to tinuro sa amin ng aming prof. So that's very wrong because again, these letters are just dummy assignments or dummy variables. It's up to you. You could use different letters for different notations.